First, we must make the TreeNode class. Inside the TreeNode class, there is an attribute of data. This is an integer. This is the data that the TreeNode will hold. Next, we have two more attributes. One is called the left child, one is called the right child. These are both TreeNodes. The constructor takes in an integer n, and upon instantiation, the data is set to n. The left child and right child attributes are initially set to null because upon instantiation, it will become a leaf node. Now we must make the tree class. As you can see, the constructor is a default constructor as it takes in no arguments. Now we must look at the addLeaf method. The addLeaf method is a recursive method that takes in two arguments, an integer called val and a tree node called node. The addLeaf method also returns a tree node. When calling this method, val is the value we want to input into the tree, and node is always the root node. First, we must check if node equals null. This is the base case. Starting with an empty tree, the root node will always be null. If this is the case, it will return the createNode method. Now the createNode method takes an integer n, and it will create a new tree node. However, if node is not null, then we have to check a few things. Firstly, we have to check whether the value inputted is bigger or smaller than the actual node's data. Since it starts from the root node, we first check if the value inputted is smaller or bigger than the root node. If it is bigger, we have to traverse right in the tree, and if it is smaller, we must traverse left. In order to traverse left, we must set the root's left child to the tree node that the addLeaf method returns when we call it again. However, this time, instead of putting in node, we must put in the node's left child. The same case is true for the right child. To visualize why this works, we can use a diagram. This diagram represents a binary tree where 10 is the root node. Imagine we want to input the number 9 into the tree. First, we must check whether the root is null, and clearly it's not null because it's 10. Next, we must check whether 9 is bigger or smaller than 10. Obviously 9 is smaller than 10, so we have to recurse left to here. So, to traverse left, we have to call the method again, but this time we must input the root node's left child. So 10's left child is 5. So now the node that we were checking is 5. So let's do the same thing again. Is 5 null? No, it's not null. Is 9 bigger than 5? 9 is bigger than 5, so we will recurse right. Recursing right is the same concept as recursing left, except instead of calling the method and inputting the left child, we have to input the right child. So this will go here. We're on the 8 now. Is 8 null? 8 is not null. Is 9 bigger than 8? Yes, 9 is bigger than 8, so we recurse right again. But now we reach a situation where 8's right child is actually null. So, if we go back to the code, we say, okay, if the node that we're currently checking is null, then we want to create a new node. So we put 9 here, and this will be the new node. Of course, here is the creation of the node. If node is null, we create the node. If the value is less than the node that we're currently checking's data, we want to recurse left. And if it is bigger, then we want to recurse right. In the end, we have to return a node in order to satisfy the return type of the addLeaf method. Now we move on to the search tree method. So this method is just going to search the tree and check that a value that you input is inside it or if it's not inside it. So we see that it takes in an integer called value, and it takes in a tree node called node, which is again the root. So first we have to check if the node.data, which is the data of the node we're currently checking, is equal to the value that you're trying to find. So if it is, we want to print out the number is in the tree. Okay. The next if statement is if node.leftChild is null and node.rightChild is null, which means that if it has no children, so there is no node to the left of it and no node to the right of it. This means that we are currently checking a root node and we are at the end of the tree, which means that if we're here and this node is not the value, then the value is not inside the tree. So if it's not either of these, then we still have to traverse the tree. So similar to the previous method, if node.data is less than val, so the current node we're checking is bigger. If the current node's data we're checking is bigger than value, then we want to traverse the tree left. If it's smaller, then we want to traverse the tree right. So this is another recursive method where it calls itself very similar to the previous one. We want to search the tree again, but this time we'll input the left, search the tree again, this time we input the right, depending on if you're traversing left or right. Finally, we have return node here as well, and this is simply so it satisfies the return type of the method.